I would ask this question on a test, and students would get it wrong, and they had good reasons to get it wrong. Okay? Danny. And the question was, suppose you are in a stable orbit. Okay? You're orbiting some planet, and you're in this stable circular orbit, and you fire your engines to speed yourself up. You fire your engines to speed yourself up. What happens to the radius of your orbit? Well, the students would do this. And I'd say you must, and this is, I think, what probably screwed them up, is I'd say you must support it with some sort of either a formula or a concept, right? And so what they would do is they would go, okay, well, if you speed up, you're going faster, right? If you're going faster, you must be closer to the planet because fast orbits are close to the planet, correct? Yeah. But that's different, right? It is true that the fast orbits, if there's a planet here, are closer to the planet, but it's not true that if you speed up while in orbit around it, that you're going to actually get closer to it. What actually happens is your inertia carries you away from the planet and you slow down. So speeding up when you're in orbit slows you down. Is that a little bit counterintuitive? Yeah, so let me explain why it is that when you speed up, gentlemen, why it is when you speed up, you actually slow down. And if you slowed down, you'd fall to a lower orbit where you'd speed up. Okay? So the first model I want to develop, and it's not my favorite, but it works pretty well, is let's use the F word. And I think we're all of us mature enough to use the F word and understand that it's not real. Okay? So let's talk about gravity. Gravity pulls us in, and the centrifugal force flings us out. Yes? Really what's going on is that the gravity provides the centripetal force to make you go around the planet. Really, right? But if you're in that frame of reference, don't you have this notion that gravity's pulling you in, centrifugal force is flinging you out, you set them equal to each other, you can solve things. It works, right? Okay? Now, let's suppose I speed myself up. So here is centrifugal force, right? Here is gravity. Bless you. Bless you. Bless you. Okay. Let's suppose I speed myself up. Well, guess what? I'm the same distance from the planet, but I'm going faster. So which one gets more? Centrifugal force gets more, right? The FC like that. Centrifugal force gets more, and I fling myself away from the planet, don't I? Yeah? Now, when I fling away from the planet, what happens to my speed? When I go away from the center of rotation, what is going to happen to my speed? All kids that grew up near Ibach Park know this. Here, slide this way. There we go. Snuggle up to those guys. Okay. What happens if I fling my arms out? What happens to my rotation rate? Slower. When I pull them in, faster, slower. There we are, right? So if I speed up, I get flung out, right? I'm going to fling out. When I fling out, I'm going to slow down. What's stronger now? If I slow down, what's stronger? It's gravity or centrifugal force? Gravity is now stronger, yes? So what does gravity do? It's going to pull me in. When it pulls me in, what's going to happen to my speed? I'm going to speed up, and I'll be going whatever that speed was, right? That new speed, right? So it's going to speed me up. When I'm going too fast, what's stronger now? Centrifugal is stronger. It flings me out. I slow down. And then gravity pulls me in, and I speed up, right? So isn't this an elliptical orbit? Fast, slow, yes? Isn't that right? Yeah. Okay. So that's a Newtonian prediction, right? Okay. So let's take a look at this. I think I've got this. All right. I'm looking for something that says orbit. Students always find it. There it is. Okay. Let's look at this guy. Stop. Okay. Strike the any key. There's like this whole scenario here. We don't really care. We just want to orbit. So I'm hitting the space bar. Time increment, I think 30 is Pepe. Okay, and then I'm going to cheat. If you hit the letter O, it beams you into a perfect circular orbit. I solved for this, right? And there's a perfect circular orbit, and around we go. Isn't that beautiful? There it is. There we go. And you can still see the little white thing there. And all I did was I solved for the orbital condition. This is supposed to be some star. I think the mass of the star is actually Earth's mass. I don't know. I just tossed that in there. And there we are, orbiting around and around. And now I'm going to, let's speed myself up. So S, I believe, speeds me up. So I'm going to go 1, 2, 3. And that flings me out. It's possible that I have escaped from the planet, isn't it? That's kind of hard to picture, but I don't think so. I think I just, there I go. Isn't that beautiful? A little round of applause there.
Oh, what's that called?
This is an elliptical orbit. It's slower here. You can actually see a little bit of it here. Right? It's like, whoa, there it goes. Right? Watch. There it goes. Okay. And it comes in. I like the ghost of it from before we teleport it out, right? Okay. So there it is. And then let's go. Let's hit the Enter key, which starts us over. Let's hit the O key, which puts us in orbit. There we are, going around and around. Okay, let's go around once. Now I'm going to hit the R key, which is retro rockets. It's going to slow us down. I'm going to hit that 5 times really fast. Okay. Well, what happens? Well, now gravity's stronger. It pulls us in. When it pulls us in, what happens to the centrifugal force? It gets bigger, which flings us out. Yes, which makes us slow down. Right? So it flings us out, we slow down. Now gravity's stronger. Gravity pulls us in, we speed up. Centrifugal flings us out, we slow down. Does that work? Does that model work for you? Yeah, there we go, right? Another way, by the way, to predict also if you're like going in a circle and you speed up, isn't your inertia going to carry you more in a straight line if you're going faster? You're harder to turn, right? That's another way to think about it. Okay? So this is the orbit lab. In the orbit lab, this is one of the things you do is describe this. Look at these 2 ellipses. Look at the 2 ellipses. How would I get back to the original one? The original one being a circular ellipse, this one being an elliptical ellipse. Right? How would I get back? Would I speed up or slow down? Slow down. Well, I slowed down to get to the lower one. So I think I want to speed up. Where do I speed up? Right where they touch at the point of tangency, and I'm going to speed up 5 times. Are you ready for this? S 5 times. Ooh, I was late. That was terrible. That was sad. I've hit it like dead on. Okay, here, I got to do it over again. Okay, here we go. Come on. Wait for it. Okay. I'm going to do it from up here. I'm going to go 1, 2, 3, 4, 5. Here we go. 1. Okay. I'm ready for the S key. You ready for this? Are you ready? Now look at that.
Oh, yeah.
Who's your physics teacher? Okay, it's a little wide on this side. It's making another track over there. That's pretty good. Isn't that pretty good? Okay, that's a beautiful thing. Now, that is one model. Are you ready for the next model?
Yes.
All right, the next model. The next model involves Einstein and relativity and mind-bending physics. Okay, so now let's have a one-dimensional universe. One-dimensional. Okay, here is a one-dimensional universe. It has length. That's the only dimension it has. Imagine you're a being in a one-dimensional universe. Are you picturing this? I could do something really enigmatic here. I could take this and I could join this seamlessly and I could make a circle, couldn't I? Are you aware of this curvature? No, you can't conceive of anything but a line, and all lines are straight for you, right? You cannot conceive of this because to picture this requires how many dimensions? Always one more, yes? Okay, so I can make a circle. Here is a one-dimensional finite universe with positive curvature. And then we end up back where we are, right? And there we are. Now, that's okay. That's pretty cool. Okay. Now, imagine a two-dimensional universe. Picture a two-dimensional universe. You now have length and width. Things are a little more spicy, yes? Isn't that cool? Okay. And so if you think about this, we can have this dimension, we have this dimension. Can I curve this guy too? Yeah, sure, I can take this thing, and if I'm like some three-dimensional being, which we are, right, I can take this two-dimensional universe and I could like create 2 points that are really in this universe far away from each other, but they could be in our universe close to each other. There could be like a wormhole between them. Are you picturing this? Right? But let's just go back to the mundane. Let's curve it in such a way that in trying to go straight, they actually go in a circle. Right? So I'm curving this. I'm taking this two-dimensional universe. I'm putting it on the surface of this globe. Here is a two-dimensional, finite, unbounded universe, correct? I'm going in one direction, and I never run into a boundary. It's not like we get to the edge of the paper, and you're like, oh crap, what's after that? Well, there's cheese after that, right? And then after that, there's peanut butter or something like that, right? Okay. Here, it's just like we keep going, and it's like it's all new to us, isn't it? Yeah? You could end up back where you started, maybe, right? Maybe not, right? Okay. How many dimensions did this take? 3. Can you picture? Okay, so this took 3 dimensions, right? What Einstein says is that matter bends space. It bends these 3 dimensions in a 4th dimension. How many people can picture that? A 4-dimensional sphere. Are you picturing it? Zzz, zzz, zzz. Like, don't try too hard, right? Your brain's going to short circuit or something like that, right? Einstein himself couldn't picture it. Einstein actually tried and tried and tried to do